Hello, my name is Luke Beall, and I'm going to walk you through a free response question from the AP Physics C Mechanics 2019 exam. So let's get started with this problem here. In an experiment, students use video analysis to track the motion of an object falling vertically through fluid in a glass cylinder. The object, that has a mass of 12 grams, is released from rest at the top of the column of fluid as shown above. The data for the speed v of the falling object as a function of time t are graphed in the grid below. The dashed curve represents the best fit chosen by students for these data. So here's the graph. We have time on the x-axis, the speed on the y-axis, and we have our dotted line for our curve of best fit. So in the first part, we want to know, does the speed of the object increase, decrease, or remain the same? And we also need to write a brief statement describing the direction of the object's acceleration and how the magnitude of this acceleration changed as the object fell. Then we're going to use the graph to calculate an approximate value for the magnitude of the acceleration of the object at a given time. Also, we're being told that the students use an equation v equals a times the quantity 1 minus e to the negative bt to model the speed of the falling object and find that the best fit coefficients to be a of 1.18 meters per second and b to be 5 inverse seconds. And so we're going to use that equation to derive an expression for the magnitude of the vertical displacement. And then we're also going to derive an expression for the magnitude of the net force exerted on the object as it falls through the fluid. And then finally, we're going to see that the students repeated the experiment with an even taller glass cylinder that is filled with the same fluid. And the cylinder is tall enough so that the object reaches a constant speed. From that, we're going to determine the constant speed, and then we're going to determine the force exerted by the fluid on the object at this time. So let's get started on this. So first, we want to know, does the speed of the object increase, decrease, or remain the same? And we're going to use the graph here that was given to us to answer this question. And this one is actually quite as simple as it sounds. So we're talking about speed, and our speed is given to us here in the in the y-axis, and we want to know, does it increase, decrease, or stay the same? Well, as we look at this graph, we see that the velocity, the speed is in fact increasing. The values are higher as time goes on. So that is a simple increase, and that question, or at least that part of the question, is done. In a brief statement, we want to describe the direction of the object's acceleration and how the magnitude has changed as the object fell. So looking at this, we want to look, instead of just the value, the y value here, or the vertical value, we want to look at the slope now. So we want to look at this point, our tangent slope of that curve is going to give us the instantaneous acceleration. And then the tangent slope here is going to give us the acceleration. And the tangent slope here is going to give us the instantaneous acceleration. So really what this question is asking, what's happening to the slope of this graph? And so if you look at the slope of this graph as time goes on, it is decreasing. Now, we want to know, it asks, is the magnitude change, does it change as it falls? And in fact, yes, it does change. And we can say, because the object is moving downward and speeding up, all right, how do we know it's speeding up? Well, we answered that in the previous problem, or previous part of the problem, that it is speeding up. The acceleration must be downward, okay? Now, let's pause for a second. Why must it be downward? Well, in order for an object to speed up, the acceleration and the velocity must be in the same direction. Okay, so let me say that again. In order for something to speed up, the acceleration, which is the change in velocity over time, needs to be in the same direction as the velocity. So we see that this speed is directed downward, or we have a downward velocity. And so if it's speeding up, that means the acceleration must be downward. And also, because the slope of the function, of the speed function here, is decreasing, that means the magnitude must also be decreasing. So it's downward, that's the direction, and it's decreasing. That answers the magnitude. Part 3 of A, we want to use the graph to calculate an approximate value of the magnitude of the acceleration. Now, because we don't have a function here, we can't calculate it exactly at t equals 0.2 seconds. That would give us the instantaneous slope, or the tangent slope. All right. We can't do that, but we can use something that we know that the secant slope is an approximation for the tangent slope. So we need to find two spots on our graph that we can use. So because we want it t equals 0.2, so we need to find something to the right and something to the left. So I need a point to the right and to the left. So if we look at this intersection here, when our curve intersects the v value of 0.8 and where our curve intersects the v value of 0.6, we can write an equation for the secant slope, which is the change in the speed over the change in time, of 0.8 minus 0.6 meters per second, all divided by 0.226 minus 0.136 seconds. And if we calculate that out, we get an answer of 2.22 meters per second squared. Now, if you were doing this because you're finding points on a graph, if you don't have exactly 0.226, that's okay. You need to have something around that ballpark in order to get the full credit on this problem. So moving on to part B, we have this model now, the V equals A times the quantity of 1 minus e to the negative bt. And we're given coefficients for A and we're given B as well. So we have values for both of those. And we want to derive an expression for the magnitude of the vertical displacement. So we have to ask ourselves, how does displacement relate to a speed versus time graph? And so when we were talking about going from speed or velocity to acceleration, we needed to take the derivative. Well, now we're going the other direction. We need to go from a velocity to a displacement. So we need to integrate. And what do we need to integrate? We need to integrate the speed function. And so we have that speed function. We substitute it in. We use this right here to substitute in there. And that is our expression for the displacement. Right now in this part, we just want to derive the expression. We don't need to plug in any numbers quite yet. We just need to get this expression to get it set up. Now, once we have this set up, we can in fact plug in the given information that we have and evaluate this integral from 0 to t. Now, you notice here that there's this dummy variable of sorts, t prime, in order to allow us to integrate and let us go from 0 to time t. And so when we do that, we evaluate the integral, we integrate the 1 minus e to the negative bt. A just comes out front because it is just a coefficient. We do the integration, evaluate at t, evaluate at 0, and we are left with our expression. Now, you could simplify this a little bit, even further, and take this to see that, all right, all of this right here, we get that 0, e to the 0 is 1, so that's just 1 over b. So we're going to subtract that through. That gives us here that 1 minus b times the quantity of e to the negative bt minus 1. And then we have that plus t and a being multiplied by that entire thing there. And at this point, we can now plug in our values for a and b that we were given up here of the 1.18 and the 5. Now, the College Board will actually give you credit for either of these answers, whether you leave it with A and B or you plug it in. Either one is up to you because those are equivalent and both would award full credit. Now we want to derive an expression for the magnitude of the net force exerted on the object as it falls through the fluid. So keep in mind, what do we have here? Our given information is a speed. You know, from the speed, we can deduce acceleration and displacement and all that. Well, how does that all relate to force? You know, what do we know about force and its relationship with those quantities? Well, we know that force is related to the acceleration. We know the net force, you know, according to Newton's second law, the net force exerted on an object is going to be the mass of that object times its acceleration. So in order to write this expression, we first need to get an expression for acceleration. So we do that by taking the derivative of our velocity function, or in this case, a speed function, with respect to time. So we're going to plug in this quantity right here, that same equation that we were using in the previous part for our speed function, take a derivative of that with respect to time, and we get the expression of acceleration is equal to a times b times e to the negative bt. Now, once again, we haven't put in any values yet because we're just working with our variables. We'll get to that in a moment. So now that we have acceleration, we have to go back to, well, how does force relate to that? Well, like we said earlier, force, net force, according to Newton's second law, is mass times acceleration. So if we just multiply by the mass, now we just introduce that mass variable into this expression, we have the force equals m times a times b times e to the negative bt. At this point, we can plug in the values that we do know. We do know that it's 12 grams, so we need to convert that to kilograms. We know that a is 1.18. We know that b is 5, so we plug those in, and we get the expression of 0.071 e to the negative 5t. That is our net force of the fluid exerting on the object. So now we're looking at this experiment being repeated. However, the conditions have changed a little bit. We're going to get a longer cylinder. And so the object, as it falls, is going to reach its terminal velocity. All right, as it falls through the fluid, it gets to a constant velocity. So we want to determine what is this constant velocity. So we have to ask ourselves, well, what's going to happen here in this graph? And if you remember, the graph had this little arc to it, okay? And we can think about, well, as time goes on, as time approaches infinity, this is going to level off, all right, at some point. And so we need to find what is that constant velocity at some really big time. So we know that after a long time, the falling object is going to reach that terminal speed. All right. And then we can find this by setting the time in the equation to infinity. So that equation that we had of a equals, or excuse me, the v equals a times 1 minus the quantity e to the negative bt. And we look at, well, really what we're looking at here is the limit. Let's look at the limit of this as t approaches infinity. And so as t approaches infinity, this right here is getting really, really big, but that's in the denominator of a fraction. So that means that this whole piece is approaching 0. So that means that our velocity, or our constant speed here, is approaching a. All right. And so you can justify this by just having the words that I had on the left, or you can justify it by using that limit and explaining that limit, analytically on the right. And then finally here, we want to determine the force exerted by the fluid on the object at this time. So for this is a question that can kind of trip you up a little bit. And we have to remember, okay, so force, Newton's law, the net force exerted on an object is going to be the mass times the acceleration. But wait a minute, at this time, the velocity is constant. So what does that mean about the acceleration? If the velocity is constant, then that means the acceleration is 0. So we can say that when the falling object reaches a constant speed in the fluid, the net force has to be 0 because there's no acceleration. All right. So because the only vertical forces acting on the object are Earth's gravitational pull and the resistive force of the fluid, these two forces must be equal. So that means that the resistive force must be equal to the weight of the object, or 0.12 newtons. So in order for this speed to be constant, there has to be no acceleration. So that means the force of the fluid has to balance out the force of gravity on it. And we know what that is. That's just the mass times the gravitational constant of 9.8, or in this case, let's just make it an easy 10, for our calculation purposes, which the College Board does accept, using the value of 10 for little g. So hopefully that was a helpful explanation of question 1 on the 2019 exam for AP Mechanics C.